Okay, so today I want to do a kind of a first project with Vivado and the ZedBoard, and to do that I want to kind of walk through just a very basic blinking light project. We're going to start off by making a new project. So I've got Vivado up, and we're going to walk through the wizard here, and we'll give it a name. We'll call this blinking light. And I keep my projects in their own kind of directory, and automatically append the project name onto your project location folder. This is a runtime logic project, RTL, and so we're going to go ahead and just leave it as that. And I'm not going to do anything at this point. We could either try to go through and select the exact set of parts that we want to include or build for, or in this case we can use one of the existing reference boards that come with the Vivado software. The ZedBoard is the first choice here, and this is actually what we're going to try to build for. So after we make our way through this wizard, we're now ready to begin the actual logic part of this thing. We know that there's 8 LEDs across the front of the board, and I want to kind of make them into a blinker that blinks from right to left or left to right. So to do that, you need to use Verilog or VHDL. This is going to be a Verilog based project, and we'll call this blinky, and we'll hit finish. Now we could go through here and enumerate all of the input ports that I want to have. So we might want to have an input, a reset. We might want to have a direction, and then we probably want to have the LEDs themselves. And so basically we can roll through this definition, or we could just type this in ourselves. This is just a little wizard to make the top module for us and save us a little bit of typing later on. Alright, so here's our module. One of the things I always do, and I wish this was almost a default, is I want to change the default net type to become none, so that way if I have a typo in the name of one of my signals down here, it doesn't impact the rest of my project. I've had that happen so many times. So especially when you're just learning, this is the way to go. Normally we would fill in this comment block, but in this case I want to make it kind of disappear, and so I'll click on this little minus sign so that it's out of my way. So now that we don't have a default net type, all of these signals need to become wires. And I'm going to go ahead and just use the output register form here, so that the LEDs become just a register, so that I can assign right into it. I don't want to have another register and then do another assign statement. It's just a little bit redundant. So basically we're going to have is an always block, and so always at pause edge clock, and if reset is equal to 1, then LEDs is equal to 1. And then basically we're just going to have direction is equal to 1. So the tab size here, the indentation, can be a little bit better. All right. So basically we just have our general logic here. So I'll fill in some comments. And so basically, normally we could just do a shift, but of course that shift is going to cause the light, the LED, to kind of fall off the end. And so I don't want to do a shift, I want to do a rotate. So if we're going to go from left to right, then the least significant bit moves over one position. Sorry, from the right to left. The least significant bit is going to move one position toward the most significant bit. So if that's the case, LEDs is equal to the concatenation of LEDs of 6 through 0. So the bit position 0 moves over 1 to the left, and then LEDs of 7. And that's actually a standard rotation. Similarly, I can now rotate from the left to the right, and as you'd kind of expect, I hope, the most significant bit is going to move one position down, and the 0 is going to wrap to become the most significant bit. So then we're going to fill in LEDs of 0 concatenated with LEDs of 6 to 1, and so this is a 7-bit field here. They're shifted down one position. Okay, so this is the basic blinky light, and at this point I could easily go in here and make a simulation for this thing. I'm pretty sure it's going to work, and just to kind of give you guys an introduction to this thing. I'm not going to worry about the simulation. We can do that in a different video. Normally at this point what we would do is go through the run synthesis, and really we want to get down to run implementation, and once we get to that run implementation, we'll be able to do the next couple of steps. This first time through we need to be able to assign each of these wires and registers to a location on the FPGA so that they can be connected to the corresponding parts on the board. So when that's all done, we'll come back. So this took just a few minutes, and at this point Xilinx Vivado has generated an implementation file, and if we were ready to move to the next step, I would go ahead and click on Generate Bitstream. But in this case I want to open the implemented design, and what this is going to do now is it's going to take me to a view of the actual kind of organization of the part. And this view is showing me all of the different sites on the FPGA, and so this is almost a 500 pin part, and we have locations A through AB, and then coordinates 1 through 22, and each one of these corresponds to a particular location on the ball grid array, which is just a fancy name for all these different locations. And so if we were to imagine this part sitting on the board, for instance, part A1 is connected somewhere. Now they're telling me some information. For example, when it says site type PS, that stands, anything that begins with that PS means it's part of the processing system. That's the onboard ARM cores that are part of this Zinc chip that the ZedBoard uses. So those are the terms. ZedBoard refers to the reference board itself. The Zinc is the name for this FPGA series from Xilinx. If we scroll down, there's another, okay, so this is a DDR, so this is PS for the DDR memory. Let's take a look at another guy here. Let's take a look at, like, say, Y. So some of these guys, like this user IO, this is available for us to use. There's no built-in assignment for one of these things. When we see this, it has decided kind of randomly that these pins here are already part of our design. And in fact, if I expand this down, we see that the Xilinx tools have kind of randomly picked pin assignments for the parts on our board, and they're not right. I mean, like, they're just kind of randomly chosen, and we need to fix that. So what we're going to do is we're going to find the Xilinx list of where things are, and to do that we'll find the master constraint file. So I'll bring up a web browser and do ZedBoard master constraint file, and we're going to look here at ZedBoard.org, and if I scroll down, so the hardware user's guide will give you some idea of where things are. And so, for example, if I'm looking for the clock, it says here that there are some clock sources on the board. So, for example, we have differential clocks, which I'm not really interested in at this point. I'm looking for the 100 megahertz clock. That's kind of our general purpose user clock. And it says here, an onboard 100 megahertz oscillator IC17 is a Fox 70 whatever part number, and that gives us a input clock to the processor logic system. This is the fabric of the FPGA, so this is exactly what it is that we're looking for, and that's going to be on pin Y9. So one of the first things I can do over here is use that to kind of assign where the clock goes. Our push buttons here, let me go back just for a moment. The power on reset signal is not exposed directly to the FPGA, like I can't use that as my reset signal because it resets the whole chip, and I just want to be able to reset this one logic. The program switch, button 6, toggles the programmer, and that initiates a reconfiguration of the processor logic. So that's not going to be a good reset switch just for this one piece of logic. The processor subsystem reset, this is connected to the PS logic, and that erases all functions. And then that's not what I want either. And so instead, what we want to be able to do is maybe just have a push button here. There's several push buttons on the board, button up, right, down, center, and left. Those are connected to the PL subsystem, whereas push button 1 and push button 2 are connected only to the PS system. So those are not exposed to the processor logic. I can't use those in my FPGA design. I could only use those from the ARM core because they're on the PS side. So we can maybe say that the center button P16 will be our reset switch. So what I often do is just write these things down. So we need Y9 and we need P16. Those will be my reset switches. Maybe what I'll do is I'll use one of these dip switches, like say switch 0 to be F22. And now I can keep scrolling down and look, here are all of our LEDs, and our LEDs go T22, T21, U22, U21, V22, W22, U19, and U14. Now, I could have easily had just looked over at the board. The board actually has all of this information on the silk screen. The systems, the parts that can be used by the logic, the fabric of the FPGA, are going to be labeled with their locations. The parts on the silk screen that are only available through the processing subsystem are going to begin with MIO, as opposed to one of these alphanumeric locations. Now, it would be great if we were ready to go. The problem is that, unlike a microcontroller, the FPGAs frequently have a very, very configurable logic block, and part of what we can do is we can actually go in and specify what voltage we're going to use for the actual I/O pins. I mean, that's kind of a completely different strategy from what we're used to seeing. Normally, you just run at whatever the microcontroller uses, and that's about it. But these are much more powerful devices. So the next step here is we can download this UCF, this user constraint file. This is the master UCF for the ZedBoard, and it'll come down as a zip file, and if we open this thing up, we can bring in this file. And what we'll see in particular are the locations that are connected to the PL side, the FPGA side. And we'll notice here that they have their I/O standard. So, for instance, this ADR0 is connected to something that requires LV-CMOS 3.3, so 3.3 volts. And if we were to keep on going down through here, for instance, here's our clock. Our clock needs 3.3 volts. If we looked at our various push buttons, the push buttons are 1.8 volt, and we got to find those LEDs. Oh, here's our switch. The switches are 1.8, and one more time here, looking for these LEDs. Here they are. LED 0 is the 3.3 volt. So it looks like everything is living on the 1.8 volt except for the LEDs. And I guess you'd kind of expect that, just because LEDs need just a little bit more voltage to manage the current. So if that's the case, we can come now and roll through this configuration, and my LED 0 is going to be U14, I'm sorry, T22, and T21 and U22 and U21 and V22 and W22 and U19 and U14. Now I gotta change all of these guys to the LV-CMOS 3.3, and it turns out because these are all one bus, I can just click on up here and make this change. Okay, so they're all set. Our clock we said was on Y9, and that's one that you'll probably end up using in every one of your designs. We said that our reset switch was going to be P16 for the button, and the direction switch, the direction switch was F22, and then the reset switch was P16. If you get this wrong, if you get the voltage wrong, oh, and we have to save this, so we'll give this a name of blinky. If we get this wrong, for example, we might get an error during the last implementation stage that the voltages don't match, and that we have, for instance, two different things on different banks with different voltages, or on the same bank with different voltage. So for instance, everything here is on bank 33, and when we change the voltage for one pin, we're actually setting the whole bank. And we have to be very careful that we don't have two things on the same bank with different voltages. The software doesn't allow for that. So while they're more powerful than a typical microcontroller, there are still some limits. Alright, so we've saved this file. I'm going to go ahead and close the implementation, and we're going to rerun this thing. Alright, so we'll rerun to implementation, and again, this will take just a few minutes. So this took another 2 minutes to go through the implementation. I'm going to go ahead and click on Generate Bitstream this time, and we'll let that go ahead and run. This will take another few minutes. By the way, you can watch the progress by kind of watching what's going on up in this little status window up here. So something unexpected happened. This comes back and it says bitstream generation failed. And so we can look at the log file, and it's kind of hard to tell exactly what happened. Instead, I'll look over here at the messages file, and we see over here that it says rule violation, unspecified I/O standard. 3 of 11 logical ports use I/O standard default instead of a specific value. And so normally we could choose to ignore this. We could go to the project settings and make this a warning. The proper thing to do would be to go here to the implemented design and change that. It's these 3 scalar ports. Remember, they said default here, and we'll actually specify what their values are supposed to be. I'm going to take a moment here and I'm going to save this file. And I'm going to go back to the project manager now. And I just want to show you that we can go here to our constraints. And we can actually modify the file as a text file. So for example, I can just copy and paste this thing to set IO property, and we'll call this reset. So this is the XDC format. We could also maybe have used the UCF format. They both do the same thing. The reason why I show you this is that there are times when this just gets kind of absurd, where maybe what we have is we have a master Excel spreadsheet of the pins and their functions and then their voltages and whatever other constraints, and then we could easily make a little macro function or a Perl program or even a C or Java program that would read that and turn it into this big list of XDC constraints. And that way maybe our database then could be used to drive this configuration instead of having to do it by hand and then accidentally have things in the wrong place. So at this point I need to regenerate all of that. I'm just going to go and skip ahead and say generate bitstream, and it says synthesis is out of date, and so that tells me it's just going to go ahead and do the whole process from the very beginning, and so this will take about 4 or 5 minutes on this computer. Okay, so at this point the bitstream is finished, and we'll go ahead and do the Open Hardware Manager to configure the board. I have my ZedBoard plugged into a USB port. It's powered on, and so now I can hit Open Target and do Auto Connect. It's going to scan the USB ports to look for any connected board. Here it found one, and now I can say Program Device. And one of the things that Xilinx drives me crazy, these little pop-up boxes that are easy to miss. I was looking around for 5 minutes trying to find why I wasn't programming my device. I wasn't hitting that one little pop-up button. What you're doing was really picking which of the different programmable parts it found. So on a complicated board you may have multiple targets that you can connect to and program. And in this case, I just want to program the zinc. Now at this point it's probably hard to read or see, but I have the board running, and those LEDs are flashing, but they are flashing at 100 megahertz, and so it's just too fast for us slow humans to see. So normally to fix this, what we need to do is slow that down, and to do that I'm going to just go back to my project manager here. I need to make some changes, so we'll go ahead and open up the blinky light project, and in this case what I want to do is I want to add a clock divider. And a lot of students, when they're first learning Verilog, they want to put that right in here, and that's just so wrong. Please don't do that. What we'll do is we'll make another Verilog file. In this case it's going to be a clock divider, and our clock divider, well, I could fill them in here, or I can just let's see, go back here, edit this file, bring him up to the front, or I can just type them in here. So we're going to have a clock in and an input reg clock out. Sorry, output. One of the other things I want to be able to do is configure the speed. Oh, I do my default net type none. Okay, and we'll get rid of this comment block. Okay. So in this case, I'm not going to have a reset switch like I did before, although I guess we could. Instead, what I'd like to be able to do is to say that initial clock out equals 0. The problem is that that would then drive that register for more than one block. And we'll find out that we can't do that. In simulation you can do that, but we can't do that in hardware. So instead, what I'm going to do is I'm going to make my own reset switch here. And so our reset logic is going to start off as 1, and then we're going to do an always at pause edge clock in, like reset is equal to 1, reset equals 0, and clock out is equal to 0. Okay, now I mentioned I want to be able to configure the number of divisions for this, and so we're going to have a parameter, and we'll call that divider, and we're going to have that equal to, say, some number like 10,000. That's going to be still too fast, but as a default that'll work. I also then want to have my standard countdown. That's going to kind of, as this thing, we count clock in edges, and so then as we count those, I want to be able to divide my clock once I reach that count. So I need a count register, and that count register needs to be wide enough to hold whatever my current parameter is, and I don't know what that's going to be. So I can use that clog2 function, and it almost universally is going to look like this, clog2, and I know that this is a system function because it's built with a $sign in front of it. And because this is a constant, when it builds this Verilog file, when it compiles it, it can actually resolve that number for what it really needs to be. So this is kind of the standard way to take a parameter, find out how many bits it needs to be. The log base 2 of a number gives you the number of bits that are required to store it. The -1 gives me the most significant bit, down to the 0 is the least significant bit. So with that being the case now, I can do a reset here if the count is equal to 0, and in here, if count is equal to divider, clock out equals not clock out. So there's our kind of standard divider. So I can now use this pretty much anywhere I want to have a clock divider. So I'll go here to my blinky light project, and we'll actually make one of these. And so my clock in is going to clock, and my clock out will be div clock. Of course, I need to make one of these, wire div clock. Of course, if I didn't have this default net type none, if I left that default, then it would automatically make div clock be a 1-bit wide wire. But this way it forces me to instantiate a wire and give it a name. Alright, the last thing I'm going to do is modify this logic down here to be triggered by div clock. And also, second last thing, I also need to give this module a name. The last thing I need to do is instantiate that parameter. And so we had it divider was 10,000. I actually want it to be like half a second. Half a second on a 100 megahertz clock is going to be 50 million. And now we are ready to go back and rebuild. So unless I have any hardware errors. I said hardware errors there, I meant syntax errors. So good news, everybody, I didn't have any syntax errors. It took about 5 minutes on this computer, and we're going to go ahead and open the hardware manager, and we'll reprogram the device. When I say things take 5 minutes on this computer, this is a really heavy-duty processor running on a solid-state hard drive, and so your mileage may vary. What may take 5 minutes for me may take quite a bit longer for you, just depending on the regular, the performance characteristics of your computer. So, I know what I did wrong. So I'm looking at the performance on the board, there's been no change, and I know why there's been no change. After I toggled the clock here, I didn't reset the count, and so of course it then doesn't actually do anything. So we'll go ahead and do that one more time. Oops. Okay, so the file was generated, and we're ready now to program our device. And I don't know if you can see the light moving around there on the camera. If I change the direction switch, we can change the direction that the light moves. Really high quality photography work here. I apologize for the crudity of the model. But there it is. There's our first project. Nice hierarchical design all the way through the tools. I'm going to do a whole bunch more of these videos. Hope you like this one. Hope it was helpful. Thanks. Bye-bye.